So we're joined today by Jack Doyle, who I will not give you his bio because his bio is going to be the podcast. We'll walk our way through some of his career highlights and talk about some things that we never talked about before on Spycast. I'm really excited about it. So welcome, Jack. Thank you for taking the time to talk to us.
Thank you, Vince. Sounds like a fun topic to get into.
Let's talk. You've had an eventful career, and sometimes we find ourselves doing jobs for decades that were somewhat accidental. And so I want to ask you, what got you into this field? Was this something that you wanted to do, or did you kind of stumble into doing, what we'll talk about, really kind of this remote sensing concept?
Well, I think you've seen in some of the notes there that I actually came to Nevada 51 or 2 years ago now, or longer. Came out in 1964 from the University of Texas, and that happened because my roommate at the time was a close friend I'd grown up with all the way back in grade school, and one of his degrees was from MIT, and he thought that the Doc Edgerton group were an interesting bunch to work with, and recommended I interview when these guys came to town, and one thing led to another, and I ended up out here, and I came to town thinking I was going to be spending a lot of time with a brand new big digital computer that they had downtown, and 3 days later I had bus tickets to the test site and found myself working in support of Los Alamos on the nuclear rocket program. And that was the start of it. But after several years of being involved as a worker bee in the direct things, an opportunity came up in which I was offered the job of being the department manager for the aerial measurement system that was pretty young at that time. It had actually started as a subcontract for the Department of Energy. They asked us to create this capability, and it came about because in the early days with cloud tracking from the test site when they were doing atmospheric testing, the U.S. Geological Survey was the only agency in the country that had aircraft that could see radiation like that in real time and could track those clouds. And they asked the Atomic Energy Commission to get them out of that business, that they were not in the bomb building business, and therefore they wanted the Atomic Energy Commission to take that job over themselves. And so they created this organization. And so I came in knowing a little bit about it, but that certainly didn't have anything to do with my own background.
You kind of stumbled into something that you turned into a long career.
It started out with, I think, 24 guys and gals in that operation, and I was the new manager there. And by the time I left that group in '96, it was like 250 people, and we had added a significant amount of capability, and a lot of things were added because of this NEST program and just emergency response in general, in addition to all of our other remote sensing needs.
Well, let's go back to the remote sensing stuff, and so people can understand the importance from a national security perspective. This is a time when you may not think, you're not just trying to detect our atmospheric tests, because in 1963 they ended. What from a national security perspective was so important about remote sensing? I mean, in your bio, you talk about the Apollo program and some of the other things that were going on during this time. So what was your day-to-day and kind of your primary focus of looking for radiation? Like, was it terrorists? Was it potential attacks on our infrastructure from a foreign power? Was it just worry that our own radiation was going to cause problems?
Well, when we started, some of the early events that we got into were things where Atomic Energy Commission, that would later evolve into the Department of Energy, were asking us to lend a hand with because of the airborne sensor capability. One of the early ones that I recall in '68, '69 was the Nuclear Fuel Services plant back in upper New York State. And they were attempting to do some fuel element reprocessing. And it turned out that didn't work out too well for them. They disposed of the liquid part of their waste into settling ponds that were not well sealed. And with our aerial survey, we were able to demonstrate that they were not well sealed. And in fact, the state of New York had discovered some deer and other animals that had high levels of products that shouldn't have been out there, things that were a result of that processing. So that's where it started out. Then we had things like the Air Force had a missile that they launched from Green River, Utah, that was supposed to impact at White Sands, and it impacted instead 400 miles south of the border in Mexico. And Mexico was eager to have it leave and not remain there, so they had hunted for it on the ground for weeks and didn't find anything. So they actually contacted us to see if we could come down and help, and it took about 3 days, and we found it for them. So,
well, you talk about things impacting in other countries that could be problematic. There's an operation that a lot of people may not know a whole lot about in Canada that had nothing to do with our systems. It had to do with Soviet satellites, and that's Operation Morning Light. I was going to wait a while to get into this, but we kind of segued that already.
Sure.
So I want to talk about Morning Light, because this is a fascinating operation that has extraordinary consequences potentially if it was not found. Because if you want to I'll let you do the talking on here, but this is a satellite system that was insanely radioactive and could have had real problems.
It was an actual operating reactor,
Yeah.
which differentiated between the kind of power sources that we launched with the Apollo program and those kind of things that were purely passive and were totally sealed and had been tested so that they could survive reentry.
Right, we use what, RTGs, or is that?
Right,
Yeah.
Radioisotope thermoelectronic generators. In the case of the Russian satellites, and they've actually have launched over the years quite a number of these. This particular one had a 40 kilowatt reactor on it, and it was connected to a piece of apparatus that was, by all definition, spy satellite, looking for ships at sea and that sort of thing. And this unit, the way it operated, the whole contraption was about the size of a bus, a large passenger bus like a Greyhound bus. And it was necessarily in low Earth orbit in order to get the high sensitivity. And it turned out that they just lost control of it electronically. They, instead of being able, at the end of the 1 or 2 year life of the thing, they were unable to control it, and they couldn't explosively separate the reactor from the rest of the spacecraft, which would re-enter and burn up. And they boost the reactor into a 500 or 600 year orbit, and that wasn't working in this case. And so nature began to take over the physics, and on the last 5 or so passes of this thing before it re-entered, 3 of those were over the United States.
Right.
And then that final one happened to be over the Northwest Territory of Canada. And so our health physics calculation showed that the reactor components could readily be deadly within 1,000 feet of them. And so there was considerable concern, and we were asked by the White House and the National Security Council, designated DOE to take the lead in that operation. And this was in 78, January of 78. And so we were on standby, had aircraft loaded. We had no idea where it would land because nobody was controlling it. And it was strictly the physics that brought it in. When it hit the atmosphere, then it started to burn up and that sort of thing. And so it re-entered over the west coast of Canada and then spread out over a 500-mile-long footprint.
Right, it didn't just land in one place, it just scattered all over.
As it melted and came apart, the fuel element, which were little tiny pellets, little highly enriched uranium pellets, as those came apart, it was like firing a shotgun from 200,000 feet, and you had these things spread over many thousands of square miles.
And it's extraordinary to think how lucky we were that it was over a relatively uninhabited area
Yeah,
versus Chicago or
yes.
New York. Or
In fact, if you look at the trajectory map that was prepared, it was over Midwest and much more densely populated areas. You also had the advantage in January in that part of Canada. It was minus 30 degrees at the border, and it was minus 80 degrees up where the thing re-entered.
use the word advantage, which I think is hilarious, because that's not an advantage for you.
No.
Having to schlep up there and grab all this stuff.
Well, none of us had ever done anything in those kind of temperatures, so our big learning curve was the isolation, and this was all before GPS.
Right.
And that made a huge difference. And we did have some systems that we had to utilize that gave us the kind of precise navigation that we needed. But the first thing that was talked about was using Loran. Well, the accuracy of Loran was Loran C, which was used by the services and many others, was on a really good day maybe a quarter of a mile, and on a bad day maybe 4 miles.
Right.
And so you just couldn't rely on that. It wasn't until years later that GPS, and that was one of the technologies that we kind of always rode right on the cutting edge of, was the use of whatever system was out there for navigation. And we went from very crude radar units that would track a single line to something more sophisticated like the inertial guidance system that was on commercial airliners, and then finally to this localized microwave ranging system that we took with us, and then on up to GPS today. And GPS has just really made that part of the job thousands of times easier.
Right. I mean, you're looking for these tiny little pellets in the middle of nowhere Canada, and you have no
Right.
way of really locking in on any kind of thing other than let's walk around and use our instruments to find this.
Yeah, and the most important thing to remember is that with radiation, there's nothing to see, smell, feel, hear, anything like that. So you're strictly relying on your sensors to locate where it might be, and so then the navigation becomes critical. If your sensor says it has seen something, then the question is, where is it? And so we really rode the progression of technology in that area. The other thing that we relied on very heavily, and this gets us into the whole remote sensing thing, was the use of camera systems. We started out just using a bank of 4 Hasselblad cameras, and we had different films in those, including an infrared film, so that we could see things in infrared that you couldn't see in the regular natural color. But by having them mounted on a unique platform that was synchronized, every time you took a picture, you were taking 4 pictures, and so you had photos that would overlay directly on top of each other. And we learned very early on that you could come up with some fascinating ways to interpret and understand that data. One of the things that we happened to do, just at a request of the again the USGS, I guess it was when Mount St. Helens was heating up before it actually had split. We overflew that with those cameras and had the infrared imagery that showed the hot spots that were developing and expanding. And some of those photographs even ended up in National Geographic.
That's pretty funny. Yeah, this is a relatively sensitive operation. It's not top secret, but you're certainly not doing things that are widely publicized, because there are some national security implications to this.
Right, and we understood those, of course. Everybody in our whole operation were cleared for basically everything. But we knew in some areas like that one that there was a public interest. Now, our aircraft overflew Mount St. Helens the day before it erupted, And we were forever thankful that we weren't there when that
Right.
happened, because we could very easily become a casualty of that.
One thing I thought was interesting that we chatted yesterday about the fact that a lot of the equipment that you used wasn't things that people were producing. It wasn't like there was a Office of Technical Services within CIA that was creating stuff for you. You kind of had to manufacture a lot of these things yourselves.
That's absolutely right. Had to design them ourselves. I mean, we needed mobile equipment that could be run off of batteries, so that we could either fly it on the airplane and, of course, hook it up to aircraft power, which was not a big deal. But even more importantly, we wanted to make some of the measurements on the ground. And so in order to move from just a radiation meter, like the yellow meters that people are familiar with from civil defense days, to a more sophisticated thing like a spectrometer, those things had to be developed from the ground up, because they were not off-the-shelf items that any of the vendors at that time had. So for many years, we found ourselves inventing things, and then when these companies would see what we had, they would get into production with those things. So that was very helpful. I mean, and as time has gone on, a whole lot more of that is off-the-shelf available. Right. But it certainly wasn't at that stage back in the 70s and 80s.
And there's not a one-size-fits-all thing either. I mean, you've got
right.
alpha, beta, gamma, all these different potential
right.
sources of radiation. What you mentioned, I think the public or people listening would, a Geiger counter, right? That's how you do it. Well, that's only a small portion of what you're looking for.
Well, there are so many sources out there in the environment. Industrial sources, natural outcroppings of things. And so, it's not enough just to get a count rate that says something there looks radioactive. You really have to identify the isotopes producing that.
Right.
And from that, then whether it's something that's significant. You can immediately differentiate, is this man-made, or is this something that's natural? And so you treat the two quite differently. If it's natural, you expect it to be there.
I think people would be really surprised to realize how much natural background radiation is out there.
When you go out measuring, you are going to find things. And so you have to, if you're in a hurry and you think you were working a threat situation, you don't have any time to resolve what it is. You need to know that right now. Right. So we had ways to do that. The other thing, too, that we found in doing those kind of surveys that started out as a radiation survey was we started finding that if you looked at the big sites, the big DOE sites, and even other industrial sites where they were working with radiation in all of its forms, including in some liquid forms, is sometimes we were looking for things not based on the radiation signature, but on the fact that we were getting an environmental signature that something was being stressed or damaged, particularly if you had underground storage tanks with things. And then there was a further spin-off out of that as we did more and more with, we moved from just film to scanners and to instruments that, again, made a real-time spectral measurement. And with those kind of things, then not only could you see hot spots or leaks or seeps or that sort of business, but then you discovered that, okay, we can look at camouflage and features like that.
Right.
Where people, it's one thing to go out and paint something in the visible color region that looks very much like the surrounding background, but somewhere in the spectrum, it's going to stand out like a sore thumb, and so you very quickly discover those. And those were features where some of the other organizations would come to us and say, we know you guys have all this equipment. Can you test this or demonstrate this for us? And sure enough, it turned out to be pretty straightforward.
It was very nuanced when you said some of the other organizations. I think it's pretty obvious who you're referring to when you're trying to...
The three-letter outfits.
Yeah, trying to beat camouflage and find things out there. You talk about Morning Light being 78. In 79, you actually led the response to what I think is one of the most misunderstood, quote unquote, disasters
Yeah.
in American history, and that's 3 Mile Island.
Yes.
I mean, just the misinformation and misperception of people putting 3 Mile Island and Chernobyl in the same sentence, it's extraordinary to me.
Yeah, they actually don't compare. The main difference being that in the case of 3 Mile Island, the containment held.
It worked.
It worked.
Yeah.
It did exactly what it was designed to do. It contained. And although there was a necessity for the reactor people to release some gases, those were all coming through what you call 100% HEPA filters, high efficiency filters. And so the only excess radiation that got outside was the kind of radiation that doesn't interact with the body in any way. It's not retained. It's what we call noble gases. And so that was a whole together different thing. If you look at Chernobyl, that first place didn't have a real containment. It had a big concrete building over it. And when the thing did an immediate transient because it was out of control, and literally was a small-scale detonation, it blew the roof off
Right.
the place. And so suddenly there was no way to control it, and so the radiation just dispersed into the atmosphere uncontrolled, and as the wind changed over weeks or two, it went everywhere.
Were you involved in any way in the Titan II disaster in Arkansas, which is so...
We actually were in Europe for a meeting at the time that occurred, and we particularly tuned in to the British humor in the papers. The farmer out there with this pointy nose thing sticking out of the back of his truck. And so even in our business, there's always the dark humor side of things.
Well, I mean,
and
there's
that
certain
goes
times
with
where
with the turf. But yeah, it turns out that that's the kind of thing that a little later, as we developed our equipment more, anytime the accident response group would deploy, we would come with them. And that group was led out of Albuquerque, New Mexico. But if we had one of our stockpile weapons, which this was in that case, the group down there would have us and others come and deploy. And of course, you're looking for the item. You don't know whether it has been exploded and come apart, or whether it's still intact, and or whether it melted and is at the bottom of the ICBM launch chamber.
Right.
So for a while there's all these uncertainties, and although we did not respond to that particular one, we certainly have responded to similar things since then.
Well, we've kind of skipped ahead. Let's talk about Nest a little bit, because Nest is... Talk about things that are misunderstood because of pop culture. I think Nest is something that pops up in certain movies from here and there about these special operations guys armed to the teeth running around shooting bad guys trying to steal our nukes. And in many cases, it's scientists who are being sent to make sure not only is there not going to be a nuclear emergency, but in case there is...
we had two roles out there. One was to help mitigate the problem in the first place, and number two was if it was already involved in an explosion or fire or something like that, then we would help with the consequence management side of that.
My favorite euphemism in the world is consequence management.
Right.
Because it is so understated. Because, yeah, sure, Arkansas was not that big. The consequence management would also apply to an actual nuke going off somewhere.
Yeah.
Yeah, and so that's
a much larger scale.
That's quite a lot more consequences to manage at that point. But
well, we had tools that were available to us before we ever left town. First of all, the NEST program was put together back in the 70s because it turned out in 1970, Ted Taylor, who had been a weapon designer at Los Alamos during the Manhattan Project days, wrote a book called The Curve of Binding Energy. And in that book, he described a crude way to build a nuclear explosive using very crude, almost kitchen tools to do that. It was a lot more simplified than the real world would have been, but the way it was laid out, it was published in a series of articles in the New Yorker magazine over a period of 8 or 10 weeks or something like that. And following that, we started to, the FBI and others started to get threats stating that they had a nuclear explosive. And after a couple of deployments that were not the smoothest things in the world because we weren't organized for doing that, the head of the military applications group in headquarters, DOE, contacted us and gave us orders in Nevada to create some kind of a response element. And so we dreamed up the name NEST, and it kind of stuck.
Well, it sort of did it. The S has changed now, hasn't it?
Yes,
Going from
yes,
search
it
team
did,
to support team.
Support, and it really was always as much support as it was search. So that what we did for real didn't change. What we called it has changed. And while it was during the days when we were actually testing weapons at the test site up until '92, we had a very large workforce to draw on to support us in all these things. After '92, when that went away, the size of the total workforce dropped pretty significantly. And so then it was decided by headquarters to later on to disperse that capability on a more broad basis. And I retired from that in '96, so I'm not as up to date on how that came about. But up until then, if something like the Morning Light or something like 3 Mile Island or any one of a number of other smaller events occurred, we became kind of the logical group to call on. So I started to say that before we would deploy on these things, we would talk to the atmospheric release advisory capability people at Livermore, who would they were using large computers, supercomputer, to take the estimated material that was being released. They would start with that, put in an estimate of what it was, how big it was, and what the dispersal mechanism was. And then they were tied in real time to the international weather system. And they would do modeling to show if there was a release, where would this plume go? And they could do that from the time of the incident, so that if the weather conditions were changing, they could keep up with that. I always said that we called them because we didn't want to fly in and land right in the middle of the problem.
Right.
And so, but the real world was to start getting a handle on how many people were at risk. So when we talk about consequence management, the first question is, what is the number of people and farm animals and crops that might be at risk from this release? And that sizes in your mind right away, how big of a deal are we dealing with? And then you proceed as you get to the site then with your capability, particularly your aerial capability. You can start to actually define where you really are seeing something. And the first thing we try to do is, of course, shrink the amount of area that has to be concerned. And we try to do that in conjunction with the local health authorities and let them communicate that to the public however they will, so that what you want to do is start reducing the number of people that are worrying about being exposed to these things.
Well, you had to scale your operations, everything from like the release of gases from 3 Mile Island all the way up to somebody smuggled a multi-megaton weapon into, or that and everything in between, right? And this is a massive project that you're asked to do.
Now, and of course, we here in Las Vegas, we're not doing the whole whole thing. We were very much part of this team that consisted of Los Alamos, Lawrence Livermore Lab, and Sandia, and the Livermore people with that ARAC were a key front end part of that operation. And even as we started to refine what we knew about the event, then they could refine their plumes as well. And if we could give them actual measurements, they would insert those and readjust what they knew about it. That system was globally capable. It got used when they had when Saddam Hussein set all the wells on fire in Kuwait. They used that system to help model that plume dispersal that you were getting with all of the wells on fire at the same time. So they could look at things that were not radiation. They could look at oil fires or other kinds of chemical releases. And any of those might have been things that we might have been pulled in as well.
You talked about working as a team. Now you were referring to Livermore and Sandia and Los Alamos. I imagine because of the national security implications of the work that you did, you worked very closely, and you already kind of alluded to this, to the three-letter agencies, to CIA, to others, because of the more you know about potential threats coming from the outside, the better prepared you can be. And of course, these agencies can possibly use the technology that you've developed to do that work overseas. I know you can, there's limitations to what you can say,
Sure.
But can you talk a little bit about the relationship that you had at DOE with NEST, with RSL, and with some of these intelligence agencies?
Well, I think you start with the fact that the whole set of issues around radiation and bombs in particular, nuclear explosives, or even nuclear dispersals of radioactive material. The rest of the community really looks to DOE, and I'm talking about the laboratories now, as well as our operational on-the-ground capabilities. They look to that family of experts as being the experts on those subjects. And other agencies, except in a limited way, made no attempt to go out and try to create a base of people and experts that would be that big. And of course, the real value we always felt was that we were, even today, the people that are engaged in that kind of research and that kind of technology. So as it changes and we learn more about it, we can, on an emergency basis, can come together and support some other operation. Sometimes it necessarily might involve a very highly skilled operator to go with a piece of equipment. And so to some degree we were prepared to do that, and I assume still are. And we did some exercises with other response organizations, both intelligence related as well as military.
It was you worked with the FBI specifically for 5 years giving this information at Quantico. I mean, that was a direct relation of kind of providing a particular three-letter agency that works on national security issues with some of the information about what you've done on the NS side.
Well, as these threats kind of kept coming in, and some of them were getting more and more sophisticated, the FBI itself realized early on that this was a limitation that they had, and they wanted their agents to know more about it, just so that when we started the initial communication on something, that they were better informed about what kind of things did we need to know, and what things could they, and how best to share those with us. So they actually, for several years there, created some special courses out at the training center at Quantico, and they would have us come in each year and talk to these groups of agents that were being trained specifically. And the idea was to have enough agents scattered around the U.S. And other locations to be brought up to speed on this, so they knew something about the subject, and that they knew about these other resources that they could turn to for help if need be. And of course, every time you do one of those kind of things, we also were doing a similar kind of a training at the Harvard School of Public Health every summer for a special program they ran that was doing training for, say, the responders at reactors around the country. And you really let them know what resources are out there that are not something that they could go easily duplicate, but which are available in the event that they have some significant problem that they need help on. And it starts with phone calls. And over the years, as a result of those things, we'd get some phone calls where somebody would say, you know, I met you at so-and-so, and I have a question. And so then that would get you started on the conversation, and then we'd remind each other how we needed to do that through the professional channels so that we kept it completely in channel with our respective organizations. And if they need to be reminded of who that contact was within their outfit, we usually do that.
How much did 9/11 change kind of the path of everything being done, from what RSL was doing to what NEST was doing to, you know, special projects here at the Nevada test site and across the board, kind of this shift to worrying about asymmetrical threats, for the fancy way of talking about terrorists, versus an accident, or versus the Soviets launching an SLBM. You know, I
And now more recently, what Hanoi might do.
Right. Well, I mean, Pyongyang. Yeah.
Pyongyang.
Yeah. I mean, I think that, you know, we've kind of now back to some of the mentality that we had, you know, in the 60s, where there's a greater appreciation of the potential for some kind of an accidental launch or a detonation, or again a dirty bomb or other things. I mean, there have been thwarted terrorist attacks where there's an attempt for a dirty bomb.
Yeah. And those have other side issues that go with them. One, if you're doing a dirty bomb with basically high-level radioactive material, the biggest threat, of course, is to the guys perpetrating
Right.
the thing, because if they don't have a very high skill level, they will be the ones that may suffer the worst consequences before they can even deploy the thing. That whole area, we've certainly, over the years, watched the progression of the way terrorist acts have gone. You know, as it started out with the attacks on the Olympic teams, then you had these hijackings of airliners full of people, even the Kilimanjaro thing with the attack on a ship, and after a while, those kind of faded away, and other threats have grown over the years, and we continue to watch those. The whole community now, all of our intelligence assets look at those things, and as we hear about any new ideas in that regard that come along, you know, we'll check our technology too to see, is there something that would apply, and is there something we need to add if we're gonna do these things.
I want to shift focus actually to a fascinating project that you worked on, that has been worked on now by different people over decades, and that is nuclear propulsion, nuclear power used to launch things into space. NASA had programs. I mean, you go back to the Orion program, where they're literally going to use nuclear bombs to launch, but also, you know, NERVA and some of these other programs that use nuclear power as a, you know, when nuclear energy was first figured out, the idea was this was going to be a somewhat dual use, a double-edged sword, where there was a nuclear weapons component to this, of course, a destructive force, but there was also going to be a very positive benefit for society. We haven't necessarily realized that as much. So I think because of some of the misperceptions about nuclear power and other things like that too. But there were a lot of attempts over the years to find very effective and positive ways to use nuclear power. And we've seen it somewhat with, like we talked about, RTGs and other things, like whether it's spacecraft like Voyager and others going to the ends of the, you know, Voyager's not using solar power, it's outside of the universe, right? It's so far away from the sun, it needs nuclear power.
The sun ceases to be of
Right.
any real help.
So how is there an appetite? Certainly, even in the height of the Cold War, where all the money was going to nuclear weapons, there were problems finding funding for some of these programs that use nuclear power or even nuclear weapons to create space travel. Is there more of an appetite now, or do you see the appetite shifting back toward potentially these programs working?
The short answer is yes. We do see it shifting back that way, and it's not for the launch of conventional things here in Earth orbit, which will continue to be done with the conventional launch engines. We did develop a fully working engine in the NERVA program, and then that program was basically closed out in '72, and a lot of that had to do with the cost of the Apollo program, the Vietnam costs, and all of that, and it reached the point where it couldn't go any further. It was a very effective working engine design, but it had a couple of very major problems. The big one was, and the original design concept was to be able to launch with that engine, and we certainly had enough thrust. We could have done that, but as they have reviewed that now into the future, what they foresee is a cluster of smaller engines, maybe 3, that would be launched into orbit conventionally, like the space station, and then assembled into a working spacecraft, and then you'd put the liquid hydrogen fuel supply on there, and you'd put the crew. And you might very well look at using that to get to Mars. We might very well look at using one or more of those engines like a tug to haul supplies back and forth to a moon base, where you might have a permanent moon base, and so you need to bring food and water and that sort of thing. And by using the nuclear engine just in space, not ever try to land with it or take off with it, but just to have it as your space source, because the fuel supply is so much simpler.
Right.
It's one thing, liquid hydrogen, and even to go to Mars, you could make before you'd have to change out your nuclear fuel in that engine, you could make about 3 round trips, and you just have to supply more liquid hydrogen.
Right, because unlike chemical propellants, which basically all that thrust that you're seeing coming out the back of a rocket ship is that going bye-bye, right?
Yeah,
Your ability to actually
right.
create thrust is what's flying
That's
out
all
the
you're
back.
doing. Yeah, the other thing about it too is that, and NASA's always paid attention to this. You look at, they have a very complicated physics term that they call impulse, which says a lot about how much payload you can lift into orbit or can move in outer space. And the impulse for the very best of the chemical conventional rocket engines is somewhere like 400. And with the nuclear rocket, even back at the NERVA days, the impulse number was like 800. So basically, for the same size and weight package, you could lift twice as much payload. And in today's world, if you really apply all of the advances in the nuclear reactor technology, going to, say, one of these liquid fuel engines, liquid nuclear fuel, you could maybe hit an efficiency that might be up in the 1200 range or higher. And so they are looking, at least 3 of the big NASA labs these days are looking seriously at nuclear power as one of the options for your deep space kind of operations. If you're going to go to Mars, you're going to take a very heavy package out to Jupiter or to Saturn. And of course, the other thing about those is with that power source, you don't have to slingshot off of Venus and back around the Earth and all that to get up enough momentum to get you there. You can actually do that, go a straight line flight, and what that does is it shortens your trip, can cut it from 2 years to 6 months or
Right.
something.
A lot of the worries when they were talking about things like ANP, aircraft nuclear propulsion, back, was the shielding issue of keeping a crew alive. I mean, there's enough radiation in space as it is.
Right, but if you're in space, the whole issue there changes a lot, because if you're here in the atmosphere, the radiation is going to be bouncing off of all of that, and so the shielding issue becomes much bigger. If you're out in space, then you don't have anything for that radiation to bounce off of, literally. And so you just have to have shielding between
Right,
where
just a
that
straight
engine
line.
is and the crew. And if furthermore you put your hydrogen fuel supply between you and the crew, that's a great shield too.
And weight doesn't matter quite as much in space as it would.
No, it wouldn't once you get it up there.
Right. Putting a massive lead brick on an aircraft
Right.
inside the atmosphere makes life very difficult. Yeah.
That makes it unusable.
Yeah. So I'm wondering if the reason that this hasn't moved forward faster than it has, or that it didn't back during the NERVA days, do you think that there is a unsolvable, and I'm going to use that word, I hope that you say no, but an unsolvable problem, the people's perception of nuclear energy?
Well, I think you're going to take a big step forward if you can say, look, we're going to launch the reactor and all that cold without turning it on, and get it into space before we turn it on. That's a big step right there, because you don't have people's image of spacecraft coming apart during launch is always going to be there. Mm-hmm. And this avoids that, because as long as you've never turned the thing on, you don't have a big radiation issue. So that's the big first step. The other thing is that at the time of those programs, one of the reasons that program shut down had to do with cost, and with the fact that from a technology standpoint, we were not technically ready to go any further than a trip to the moon. We weren't ready to go to Mars or send very complex packages to the moons of Jupiter or Saturn. And now we are. And so as we think about those now, then the issue becomes, well, chemical rocket to do those things is absolutely huge. And the materials you're using are so complex that there's no way to make those at the end of your trip for a return or something like that. So you needed something like the nuclear engine that would give you longer legs. And so I think all those things can be overcome.
Let me wrap this up by asking you, going back to on the nuclear verification side, there's obviously a lot of conversation, and we don't have to get specific about countries, but a lot of conversation about emerging nuclear powers, or the worries about emerging nuclear powers. Mm-hmm. And a lot of people don't quite understand verification, like why we think we can actually tell if someone's becoming an emerging nuclear power, or how far ahead North Korea is in their system. I mean, the last North Korean underground test, they tried to boast that it was a fusion bomb, a thermonuclear one, within an hour. We said, nope, nice try. It's exactly the same, seismic readouts and even spectroscopic readouts as your fission test that you did before. Are we in a position where we have the technology basically to know just about what anybody's doing and verification process? I mean, that's where we can get specific. Let's talk about Iran. The idea that we can keep track of what is going on through what we would call massive intelligence world, or remote sensing, that seems to be pretty close to reality at this point. We've gotten pretty good at that. What do you think?
I think that's true. We can certainly differentiate pretty well between sizes of yields that we get, and of course there's other parts of that signature. It's critical that the people trying to do that are doing it in a contained fashion. They need to do it because that's what the world demands, but they also need to do it because if there is any release of anything, that'll be our best clue of what just happened.
Right.
And there are a variety of ways to capture that. And it's not all. Certainly Nest is only small portion of that operation. We may help analyze what comes out, but we don't need to be part of the front end of it.
Mm-hmm.
But yeah, the real critical factor is the access to the nuclear material that it takes to do one of those things. And as far as the technology, it's pretty much out there at this stage of the game with enough highly trained physicists and whatnot to know how to make the basic steps.
Mm-hmm.
But then trying to get something that's small enough and light enough that you could transport it somewhere.
We got to deliver it.
That's a whole different story. Now that gets a lot more complicated to do. And so you look at everything. I mean, you look at all the interrelated pieces, and it certainly helps to have that be kind of an integrated team looking at that, so that you say, okay, in their tests they look like they've created a bomb that's a certain size, and then the question is, how much does it really weigh, and what kind of configuration is it in, and really fit on any of the launch platforms that they have for delivering it. Of course, they don't have to deliver it with a rocket. If they could make one that was small enough, they could take it apart maybe and move it in pieces,
Right.
and get it next to the target and then put it back together again. That's really the one that you'd worry about the most, I think.
We talked a little bit about, and then we'll wrap up. I've taken way too much of your time, but I could talk about this stuff forever. We talked about working as a team within not only the nuclear weapons community, but also within the USIC and others. What about your equivalents overseas, within the allied nations working together? Was there a lot of international cooperation in developing the technology to do a lot of this, but also kind of breaking up the world? You talk about worldwide coverage, but is there a British version of Nest that was around the same time, or a French version, or German, or even the Russians to try to do this?
Some of that I would have trouble elaborating, but the short answer is yes. There are other capabilities out there, and I think the biggest advantage is having us try to work together. There are many things that keep us from doing that, of course, with depending on international relations at the time. And we still, our Atomic Energy Act says we don't share detailed nuclear technology with anybody except through very prescribed pathways. And really the only country that we've historically done that with has been the UK. And we have a 50-year history of working with them on testing. A lot of their testing was done in conjunction with us here at the test site and out in the Pacific in the early days. But other than that one country, we're much more limited in what we could share with others. But we certainly have tried to collaborate and coordinate with others if they were interested in doing that.
Well, Jack, thank you so much for taking the time to talk to us on Spycast. This is a fascinating conversation, and we really, truly appreciate your time.
Well, it's been very interesting, and my first one of these kind of things. I've certainly visited with others, but never to do a podcast. So,
we're very, very thrilled to be your first, so we appreciate it. Thank you.
Great.